Hello, I am Seema and welcome to part 16 of the chapter, The Solid State. In the previous video, we were discussing the imperfections in solids and I talked about crystal defects and I told you the broad categories of the crystal defects. I told you that there are three types of crystal defects. The first is stoichiometric defect, the second is non-stoichiometric defect, and the third is impurity defect. In this video, I'm going to be discussing the first kind, that is, we'll be talking about the stoichiometric defects. If you remember in the previous video, I also told you that stoichiometric defects are of different types, and there are again two types of solids or crystals which show these defects. Solids that are non-ionic in nature show stoichiometric defects, which are known as the vacancy defect and interstitial defect, and solids that are ionic in nature show Schottky and Frenkel defects. So we'll be discussing all of these one by one, but first let us come to the basic, when we talked about the stoichiometric defects, I told you that these defects are also called intrinsic defects or thermodynamic defects. So let me first explain why are stoichiometric defects. First, by definition, a stoichiometric defect is a defect which does not affect the stoichiometry of the compound, or the stoichiometry of the compound remains intact. It is preserved. When even after the defect, the stoichiometry is not affected. Therefore, they are called stoichiometric defects. They are also called intrinsic. Intrinsic is because whatever the defect is, it is due to the compound or the solid or the substance itself. There is no external source that is causing these defects. So they are called intrinsic defects, that there is nothing external that is causing. For example, in the case of impurity defects, the impurity is an external substance which is causing the defect. So that is not intrinsic, that would be extrinsic. So these are stoichiometric defects, do not have any external cause of the defect. So they are called intrinsic defects. They are also called thermodynamic defects. The reason that they are called thermodynamic defects is that according to the third law of thermodynamics, a pure or perfect solid, absolutely ideal solid, can only exist at 0 Kelvin. At higher temperatures, there will always be more entropy, and when there is more entropy, there will be more disorder. A perfect crystal would be one which is perfectly ordered. There is perfect order in every place, every point of the crystal. There are no point defects, there are no line defects, but that is possible only at 0 Kelvin. So any temperature above 0 Kelvin is not thermodynamically feasible for a perfect crystal. That is why when I talked about crystal defects, I told you crystals are never perfect. There is always some defect in the crystal. Even in the case of diamonds that you find that take millions of years, a very long period to crystallize, the slower a crystal is formed, the purer and larger it would be, yet that crystal would also have defects because it has not been created at 0 Kelvin. So that is why they are called thermodynamic defects. They are also called intrinsic defects. And these are defects that do not disturb the stoichiometry of the compound, and that is why they are called stoichiometric defects. Let us now come to the two types of solids and the types of stoichiometric defects shown by them. When you have non-ionic solids, there are two types of stoichiometric defects. One is vacancy defect and the other is interstitial defect. Let us come to the first one, that is vacancy defect. When you go looking for a job or you're trying to apply for the post of a school appointment in your school, if that post is empty, only then would they consider you for that post. Isn't it? So if there is a vacancy available, when you're looking for a job, what do you look for in the newspaper or on the internet? You look for vacancies, job vacancies. So wherever there is a vacant site, that is where you can go and you can fill up that place. If there is a vacant seat, you can come and sit on that vacant seat because it is vacant. If it is already occupied, you might not go and sit on that seat. So just as the name suggests, vacancy defect, a defect that is causing vacancies, right? So when some of the constituent particles do not occupy the lattice sites. What is a lattice site? In a solid, every place where one of the constituent particles should be present is known as a lattice site. If I imagine this to be the solid, every corner, let us assume, has an atom in the cube, in the cubic lattice. So every corner should have an atom. So every corner should have that particle. In vacancy defect, what happens? Some particular lattice point, these are called lattice points. Every point where there should be a particle is a lattice point. Some of the lattice points are vacant, they are empty. So when the crystal was being formed, some of the sites were not filled up. So they remained vacant. Or sometimes what happens when you heat up a substance, some of the components may get vaporized and they may leave the lattice point. So a vacancy defect, that is created either when the crystal is formed or when you heat up the substance. And some of the volatile, if the substance is made up of, the solid is made up of volatile substances or volatile compounds, they may evaporate and they may leave a missing lattice point. So vacancy defect, when some of the lattice sites are vacant, it is known as a vacancy defect. It can be caused, it can be developed when you heat up a substance, or it can be developed when the substance was being formed. How does a vacancy defect affect the density of the substance? What is density? Density is mass per unit volume. You already know this. Let us assume that both of these are exactly the same size. Now, although my drawing skills are not made to scale, these two diagrams are not made to scale, but imagine that they are both the same size. In this solid, how many constituent particles are present? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12. There are supposed to be 12 constituent particles. Let us say each constituent particle is 1 gram each. And let us say that this is 1 cubic meter. It's not a cubic meter, but let us assume that it is 1 cubic meter or centimeter or whatever. Centimeter, maybe on your screen you're looking at it as a centimeter. So what would the density be? It would be 12 grams per centimeter cube, because it'll be a cubic solid. It will not be actually in two planes. So density is mass per unit volume. If two of the sites are missing, they were supposed to be 12 cubes. They were supposed to be 12 cubes, but out of 12, only 10 are present. Then the mass of two of these cubes will be less. That much mass will be less per unit volume. So, in other words, if the mass is less, density will decrease. So, whenever you have a vacancy defect, it affects the density, that it decreases the density, mass per unit volume. When the substance itself is missing, then the mass goes down and the volume remains the same. So mass per unit volume decreases, that causes a decrease in density. So that was vacancy defect. Excuse me. Let us now come to the second type, that is the interstitial defect. Interstitial, what are interstitial spaces? Spaces between constituent particles. Do you see this? The interstitial spaces. Spaces between the atoms or molecules, whichever is making the solid. What happens in an interstitial defect is that sometimes the particles are arranged in such a manner that some constituent particles occupy the interstitial sites. Instead of occupying the lattice points here, you see the 12 balls are already present. 1, 2, 3, 4, the black balls. And these two red balls are just occupying the interstitial spaces. They are just present in between somewhere. So they are occupying interstitial spaces. Therefore, such a defect is known as interstitial defect. When some constituent particles occupy the interstitial sites, the lattice points are all filled up, but some of the particles, they go and they enter the interstitial spaces and they just sit there. While the crystal was being formed, they did not get enough time to really escape and reach a lattice point. They just sat between the lattice points, and they are kind of like an impurity. An impurity would be something that is not the constituent particle. This is not an impurity, external impurity. It is the same substance, but the molecule is not occupying a lattice point. It is occupying the void. It is occupying the empty space. So there should have been 12 balls in this volume, or imagine it to be 12 cubes in this cube. But there are 2 additional ones. So the mass of this cube or this solid, if it was the same volume, is more. The mass has increased. The volume remains the same, but 2 additional component particles are there, which are causing an increase in mass. So mass per unit volume increases, so interstitial defect will cause an increase in the density. Is it clear? The mass per unit volume in interstitial defect increases, which causes an increase in density. The mass per unit volume in the case of vacancy defect decreases, therefore it causes a decrease in the density. So these were non-ionic solids. Let us come to the other category of solids now, that is ionic solids. Ionic solids also actually show the same defects. The only difference is whenever you have an ionic substance, when it exists, it has to maintain its electrical neutrality. Imagine, common salt is an ionic substance. If it had the number of positive and negative charges are equal, therefore it neutralizes. They neutralize each other. Imagine if there were more positive charges or more negative charges in ionic substances. If you touch them, you would get an electric shock because one of the charges is more. So electrical neutrality always has to be maintained in the case of ionic solids or ionic substances. That is why when you see the same defects, they have to adjust, or the defect has to exist in such a way that the number of positive and negative charges are equal in the ionic solid. So these defects are known by the names of Frenkel Defect and Schottky Defect. Frenkel Defect is actually both of these defects, a kind of a combination of both of these defects. Let us see what happens in Frenkel Defect. We know that usually cations are smaller than anions. This is something that you've already studied. So in grade 11, that cations are usually smaller than anions. Anions are larger in size. So usually the smaller ion, which is usually the cation, is dislocated from its lattice point. Imagine this solid. This is supposed to be an ionic solid. The number of positive and negative charges should be equal. Positive, negative, negative, positive, right? Plus, minus, plus, minus, plus. So this will be plus, minus, plus, minus. This will be minus, plus, minus, plus. That is alternating positive and negative charges. That is how the solid will be formed, because in ionic solids, there is no bond. They are only attracted to each other due to opposite electrical charges. A cation will be attracted to an anion will be attracted to the next cation, and so on, and thus they all remain together. So what happens, imagine this to be the solid, that positive and negative charges are equal and the solid is formed in this manner. So the smaller ion, which is usually the cation, this was the site where a cation should have been present. Do you see? Minus, plus, minus, plus. Then with plus you have a minus, plus, minus, plus. So this should be a minus. There should be a plus, that is a cation should have been present here. But the cation is smaller in size. So what happens? The cation was supposed to be here, but because it is so small, it kind of slips between into the interstitial space. It slips away. Because the space, interstitial spaces are large enough. And imagine if the balls were not of the same size and you had a little small sized ball, which was supposed to be here. Then the spaces between these balls would be so large that that little ball can easily slip into the interstitial site, thereby leaving its lattice point. So when it leaves the lattice point, it causes a vacancy defect. But when it enters the interstitial space, it causes the interstitial defect. Right? What is happening here is that first a what is it called? A vacancy defect is created, and then that vacancy defect, whatever created the cation that moved, that caused the vacancy defect, created an interstitial defect by entering one of the interstitial spaces. This kind of a defect is known as Frenkel defect. So the smaller ion, usually the cation, is dislocated from its lattice site and from its normal site and enters an interstitial site. It creates a vacancy defect at the original site. This was its original site. It created a vacancy defect here, and it caused an interstitial defect at the new location. Wherever it went at the new location, it created an interstitial defect. Since no particle left or entered, there is no change in the mass. In this volume, the mass remained the same. The number of particles did not change, or it only shifted its position. Therefore, there will be no effect on density. Mass per unit volume remains the same. If this was the volume, the mass has not changed. Therefore, such a Frenkel defect does not cause a change in density. And since the positive charge did not leave the crystal, therefore, the number of positive and negative charges is still the same. Therefore, the electrical neutrality is maintained. Right? So that was Frenkel defect. We now come to the Frenkel defect is also called dislocation defect. Dislocation because the cation got dislocated. It changed its location. And it changed its location not in a way that, okay, I'm going to change my house, I will not live in this house. I bought a new house across the city, so I'm going to go and live in that house. They are proper lattice sites from one house to the other. But if I got dislocated, and I moved out of my house and I did not go to another house and I came out on the street, then that would be Frenkel defect. I moved from my lattice, I got dislocated from my own site, but I did not move into another lattice point. I got dislocated from my location, I have moved away to a wrong location. This is not its actual location, yet it is present there. So this defect is also known as dislocation defect. There is no change in density. I explained this to you. It is shown by, now, which compounds would show this defect? Obviously, I told you the cation is smaller in size. Whenever you have a large anion and a small cation, the size between the cation, so a large anion and a small cation, when the size difference between the cation and anion is large, such compounds will show Frenkel defect, because it will be very easy for the small little cation to slip away from its lattice point and occupy an interstitial site. So now we come to the last stoichiometric defect, which is known as the Schottky defect. Schottky defect is also seen in ionic solids. What kind of defect is this? This is a kind of vacancy defect. It's a proper vacancy defect. That is, the ions are missing from the compound. Did you see they were empty sites? The same thing is seen here also, that there are vacant lattice points. But why is it then different from vacancy defect? Why do we study it differently? Because in vacancy defect, there is no electrical neutrality that had to be maintained. In this defect, the number of positive charges that is lost has to be equal to the number of negative charges lost. Ultimately, the solid should still have equal number of positive and negative charges. So, if you imagine the cation and anion to be single positive, one positive charge of cation, one negative charge of anion, then equal number of cations and anions should be missing. So, Schottky defect is a vacancy defect in which the number of missing cations and anions is equal. Therefore, these missing pairs of anions and cations, they are known as Schottky pairs. They are known as Schottky pairs. Why Schottky? They are causing Schottky defect, which is a vacancy defect, but number of cations and anions that are missing is equal. Again, since the ions, constituent particles, are missing from the solid, if you imagine this cube is missing, this cube is missing, this was positive, this was negative, then two cubes are missing, so it will affect the mass of the whole cube. right? So if two of the constituent particles are missing, the mass of the cube will of the entire solid will be decreased, but the volume remains the same. Therefore, Schottky defect causes a decrease in density, just as vacancy defect causes a decrease in density. Then I told you that these pairs of cation and anion which are missing are called Schottky pairs. Sodium chloride usually shows Schottky defect. And in sodium chloride, usually in 1 centimeter cube, if you imagine one of these cubes, 1 centimeter cube of sodium chloride crystal, there are usually 10 to the power 6 Schottky pairs. 10 to the power 6, that is 1 with 6 zeros. Those many cations and anions, sodium and chloride ion pairs are missing. Therefore, imagine when the number is so large in one cube, although to form 1 centimeter cube, there would be so many of these ions, yet 10 to the power 6 is a large number for the Schottky pairs to affect the density of sodium chloride. Schottky defect is shown by other solids, other crystals like sodium chloride, potassium chloride, cesium chloride, silver bromide, and if you notice, silver bromide shows both Frenkel defect and Schottky defect. Because the size difference between silver and bromine is large, silver can slip into the interstitial sites showing Frenkel defect. Yet, it is also possible that silver and bromine both are missing, causing Schottky defect. Right? So these were the different kinds of stoichiometric defects seen in solids. With this, I'll wind up today's video. In the next video, we are going to talk about the non-stoichiometric defects and the impurity defects because they are not as extensive. So if you wish to watch other videos of this chapter, please click the link that appears on top of the video. And if you found this video helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.